Okay, welcome to the Aspirin lab pre-lab to give you the information on how to do the calculations and some general notes on the lab procedure in case you've been absent due for one reason or another. The lab is divided into two parts. First of all, in the first part, lab 38, you're synthesizing the aspirin, and lab 39, you're analyzing it. Now, for the synthesis of aspirin, for that first part, this is the reaction showing the synthesis of aspirin. Salicylic acid plus the acetic anhydride makes acetylsalicylic acid plus the acetic acid. The only calculation that you need to do for this portion of the lab is a percent yield, mass of what you actually got over mass of what you theoretically should have gotten stoichiometrically. And for the percent yield calculation, base that please off the mass of your recrystallized aspirin, not the mass of the aspirin based on the initial crystallization. You want to do it based on your basically on your best sample of aspirin, your purified aspirin. Now, there are two reactants, the salicylic acid and the acetic anhydride, so you're going to have to figure out your theoretical yield. The lab tells you, that lab handout tells you which one, the salicylic acid or the acetic anhydride, is in excess. So therefore, the one that is not in excess is the one that's limiting. I'm not going to tell you that. You need to go back and look at that. Once you figure that out, which one is in excess, the other one will be limiting. You can figure out how many moles of that you used based on the lab that you did, and convert that into moles of product of the acetylsalicylic acid. This reaction is balanced. As you can see, everything is 1-to-1. And then once you get moles of product, you get grams of product, and that's going to be your theoretical yield. You're going to compare that to your actual yield to get your percent yield. So that's fairly straightforward. The second part of the lab, the analysis of aspirin, we run into a little bit of a problem. The acetylsalicylic acid is not the only acid in the sample. As you can see from the previous slide, when you make acetylsalicylic acid, you're also making acetic acid. And you also probably have some leftover acid, some unreacted reactant that's still there. There are multiple acids in your sample. We are going to be reacting the aspirin sample with sodium hydroxide. Now, sodium hydroxide, because it's a base, it doesn't particularly care which acid it reacts with. It's just going to neutralize all acid that it comes into contact with. So what we're going to be doing for the analysis of aspirin is that we are going to react sodium hydroxide, which is a base, with our sample, which contains multiple acids. The sodium hydroxide will neutralize all of the acids. We are then going to add excess sodium hydroxide. The reason we're adding the excess sodium hydroxide is because the excess hydroxide will only react with the aspirin sample. It will only react with the product of the original aspirin neutralization. We were then going to perform what is called a back titration, where we're going to now add hydrochloric acid into the sample, and we're going to figure out basically how much excess sodium hydroxide was added. The excess sodium hydroxide will only react with the aspirin derivative that we've created, and we're going to use that information and then we can figure, by adding hydrochloric acid, we can then use that info to figure out, okay, well, how much of this aspirin realistically was initially aspirin. How much of this acid was aspirin versus how much was the other acids in this sample. Fundamentally, in the analysis of aspirin, there are three things that you're doing. The first step is the neutralization of the aspirin sample with the sodium hydroxide. Now, I've vastly simplified the formula for aspirin here. I do not want to see it written as HASP on your lab report. Please figure out the formulas. The lab packet has this information. I'm just simplifying this so that we can sort of see what's going on. In the first step, where you do the neutralization with the sodium hydroxide, It's a standard titration. You're going to be using phenolphthalein. You're going to dissolve the aspirin. You're going to add sodium hydroxide into it until the sample turns faintly pink. You have done this before. You're creating water and you're creating acetyl salicylate. That's the conjugate base of acetyl salicylic acid. This is the reaction that happens with the sodium hydroxide and the acetyl salicylic acid, but the sodium hydroxide will react with all of the acids in the sample. So this is like a complete neutralization for all of the acid impurities that are in our little aspirin sample. So step 2. We're now going to rapidly add excess sodium hydroxide. This is not a slow and careful titration. This is like adding just a whole bunch of sodium hydroxide all at once. And what this will do, this excess sodium hydroxide, it will react with the conjugate base of the aspirin, the acetyl salicylate, and it'll hydrolyze it. It will split it apart. Right? Hydrolyze, meaning to lyse something or to break something through the process, in usually water, but in this case the hydroxide is the thing that's doing the hydrolysis. The excess sodium hydroxide splits apart the conjugate base into two components, and we have additional, notice we have additional OH minus left over. Now, the excess hydroxide ion doesn't do anything to the other acid impurities that we know we have in the sample. It does not hydrolyze them. So this is what is specific to the aspirin acid on its own. In the third step, this is our back titration. We still have the same flask. We titrated initially with sodium hydroxide. We then added a whole bunch of excess sodium hydroxide to hydrolyze the aspirin's conjugate base. Now we want to figure out how much of the hydroxide we added in excess. This is the back titration. We now have all this excess OH minus here, which we are going to now react with hydrochloric acid here to make water. That's what the back titration is. You're going to have two burettes. You're going to have one with sodium hydroxide and one with hydrochloric acid, and you're going to be moving your flask from one to the other. This last portion will allow us to determine, through knowledge of how much hydrochloric acid we added and the molarity of the hydrochloric acid that we added, it will allow us to figure out how much OH minus we had left over, and that is going to be what's going to allow us to calculate how much acetyl salicylic acid is in the sample. So three major things: initial neutralization with sodium hydroxide, which will neutralize all the acids; adding excess sodium hydroxide, which will break apart aspirin's conjugate base; and then we're going to do the back titration to figure out how much sodium hydroxide did we need to break apart aspirin's conjugate base, and then kind of work backwards from there to figure out how much of aspirin's conjugate base and therefore how much aspirin we had. The calculations for the analysis of aspirin really boil down to this. I'm looking for the percent purity in your aspirin sample. And basically percent aspirin. It's very straightforward. It's like other things we've done this year. It's mass of aspirin divided by mass of the sample. The mass of the sample is going to be determined in the lab. It's based on the individual trials that you're doing. And the mass of the aspirin, the grams of the aspirin, is going to be determined through getting moles of aspirin, obviously. Hopefully we can see that. You can determine the molecular weight of aspirin on your own. I'm not going to tell it to you here. You have the information to do it, so you can calculate it. So the bottom portion, gram sample, that's going to be from the balance. And the mass of the aspirin is going to be coming from moles of aspirin, which is then derived from further calculations through the back titration. So just to kind of let you know that this is really the big result that I'm looking for you to calculate for the analysis of aspirin. It's the percent aspirin in your sample. So how do we get moles of aspirin? Because that's really the big question. Because if we can get moles of aspirin, then we can get grams of aspirin, no problem, and then we can get the percent purity in the aspirin sample. So analysis of aspirin, the calculations. First of all, we are going to be using the sodium hydroxide that you standardized before because we're going to pull in normality again. We're going to pull in the idea of equivalence. First of all, in the first titration, where you are neutralizing all of the acid impurities in your sample through the sodium hydroxide, you can figure out how many equivalents of sodium hydroxide you needed to do that. It's very straightforward. You just do the volume of your sodium hydroxide, which by the way has to be in liters, not milliliters, times the normality of your sodium hydroxide, which you standardized, and you know that to 4 decimal places. And that's going to give you the number of equivalents of NaOH that you needed, which will tell you then the number of equivalents of all acid. Right? Because this is the sodium hydroxide that was needed to neutralize all the acid. So, you know, that's telling you how much total acid you have in the sample. Our problem is that we are looking for very specific acids, so we can't use that number to turn into moles of aspirin to grams of aspirin. So we need to go to this next step. Now we're going to look at the amount of hydrochloric acid that we added. We're going to do the same thing. We're going to say in the back titration, which is step number 3, I labeled it, it correlates with the previous slide, or I think two slides ago. We're going to take the volume of hydrochloric acid that we added in the back titration. Again, this is in liters. We're going to multiply it by the normality of the hydrochloric acid. Don't worry, this will be provided. You do not need to standardize the hydrochloric acid that you'll be using. I will tell you what the normality is. And that's going to, if you multiply the volume times the normality, that's going to give you the equivalence of the hydrochloric acid. Well, why is that significant? Why do we need the number of equivalents of the hydrochloric acid? The number of equivalents of the hydrochloric acid tells you how much excess sodium hydroxide you had, because this is reacting, this is the H plus OH minus makes H2O. The number of equivalents of HCl is equal to the number of equivalents of excess sodium hydroxide. So we have like all the sodium hydroxide is here, right? This is all. And then we have excess down here. It then becomes fairly straightforward, well, the calculation is pretty straightforward. As I said before, number of equivalents of HCl is equal to the number of equivalents of excess sodium hydroxide. Why do we care about the number of equivalents of excess sodium hydroxide? Because of here. The number of equivalents of excess NaOH that we have correlates with the number of equivalents of acid not broken down by the base hydrolysis. Number of equivalents of acid not broken down by base hydrolysis, that's all acids except aspirin. So the first calculation tells us how much NaOH we had total, i.e. how much acid we had total. This portion tells us how much acid we have except for the aspirin. So therefore, the difference between the total number of equivalents of NaOH from the first step and the number of equivalents of excess NaOH from this part will give us how many equivalents of acetylsalicylic acid we have, i.e. all you need to do is subtract the two numbers. You subtract the you find the number of equivalents of NaOH from the first step, which represents all acid, excuse me. You subtract away the number of equivalents of excess NaOH from step 3 from the back titration. That represents all the acids except the aspirin, and what that will give you is the number of equivalents of NaOH that was used to neutralize the aspirin. Because aspirin is monoprotic, that's important, the number of equivalents of NaOH you use to neutralize the aspirin is equal to the number of equivalents of the aspirin itself. So it really is a straightforward calculation. The theory behind it is complicated, but the calculation itself is very easy. Find the number of equivalents of NaOH used in the initial titration, find the number of equivalents of hydrochloric acid used in the back titration, subtract the two, and that will give you the number of equivalents of aspirin in the sample. Aspirin has one equivalent, therefore the number of equivalents of aspirin will be equal to the number of moles of aspirin. You can turn moles of aspirin into grams of aspirin. And again, we are looking for this purity, percent aspirin in the sample, mass of aspirin over mass of sample, which again is going to come from the balance. Multiply that by 100, and there you go. That's going to be your percent aspirin. A few notes on the procedure. You're going to do this 3 times, this whole process. You're going to do it 3 times so that you can get 3% aspirin so that you can take an average percent for the purity of your sample. You're going to use about half of a gram of aspirin sample each time. I said use the fancy scale. We want to use the obnoxious balance that goes to 4 decimal places when we're doing this because it's going to give us much more precise information. If you don't have enough aspirin to do, if you basically have less than 1.5 grams of aspirin, which is the minimum amount that you need to do this, ration your aspirin, turn it into 3 different trials. You know, maybe you need to do 0.3 grams instead of 0.5 grams. Ethanol is going to be our solvent here because it is a somewhat polar solvent, and aspirin is a somewhat polar molecule, so they work well together. In the first step, in that initial titration, where the NaOH is neutralizing all of the acid, phenolphthalein is going to be our indicator, and we're going to titrate in the sodium hydroxide until we get that faint pink color. You're going to figure out how much NaOH you just added. You can easily get that information from the burette. Then, for the second step, the adding of the excess sodium hydroxide. You add 15 milliliters to the volume you just added and add that total amount now to the aspirin sample. For example, I put an example up here because I think it's difficult to describe in words. Say you needed 13.5 milliliters of sodium hydroxide to get that nice faint pink color. And by the way, I made that number up. I do not know if that's the approximate volume for the titration, so I'm putting warning lights on this. Is simply an example. It's not. This is not a suggestion that that's how much it's going to take. Say you needed 13.5 mils of the sodium hydroxide to reach the faint pink color. Great, that is step 1. You now need to add excess sodium hydroxide. So you're going to add 15 milliliters to that volume. So 13.5 plus 15 is 28.5 mils. You add an additional 28.5 milliliters to your sample. So we do the initial titration where you added 13.5 milliliters. That's step 1. Step 2, you're now going to add an additional 28.5 milliliters of sodium hydroxide to your sample. So at this point, we've got just shy of 45 milliliters or so of sodium hydroxide added into the flask. It is adding a lot of NaOH. That is the point. That's how we hydrolyze the aspirin. For the third step, after you add the excess sodium hydroxide, it says something like you heat it up in a hot water bath and then you let it cool down. There's a lot of that in organic chemistry, which is what we're doing. This is an organic chemistry lab. A lot of heating and cooling and kind of waiting around. You should probably re-add the phenolphthalein at this point. You want your solution to be a hot pink. We have lots of excess NaOH, so this should be a very basic solution. If your solution isn't pink, it just means that you need to re-add the phenolphthalein. It might have deteriorated in the process. And on our third step, that back titration with the hydrochloric acid where we figure out how much excess sodium hydroxide we had, we're adding HCl into the flask. And because we are starting with a base and adding in an acid, we're not going to do the titration until the faint pink color appears. We're going to do the titration until the faint pink color disappears. Right, because it should be hot pink and we want to turn it colorless. Okay, that's my pre-lab. Those are my notes on how to do the calculations. I'm going to leave the video up and leave the PowerPoint slides up for you to peruse at your leisure. You may ask me for help with the calculations, but I'm going to demand to see your notes from this prior to, so it's basically I'm not going to answer questions in the calculations unless you can prove to me that you have watched this, and even after watching this you still don't understand. Okay, so good luck with this. Hope it goes well.